Good afternoon.
Good afternoon, sir.
Sorry, missed yesterday. What were you supposed to have gone for today? This is not done, but let's cover up for yesterday what we had to meet to attend to, and that is vapours. We are supposed to start on vapours. So we are looking at vapours. To start with is what we call a saturated vapour. A vapour which is saturated is one which is said to be in dynamic equilibrium with its own liquid. This is a vapour which is in dynamic equilibrium with its own liquid. So the vapour is in contact with its liquid, and they're in what we call dynamic equilibrium. Then it is from here that we attain what we call saturated vapor pressure. So such a vapor can exert a pressure upon a liquid or upon a cover which is maybe covering the liquid. So you can say saturated vapor pressure. Now the first one was a vapor. Now this is a pressure. So this is a pressure exerted by a vapor, which vapor is in dynamic equilibrium with its own liquid. So this is a pressure exerted by a vapor which is in dynamic equilibrium with its own liquid. Some books you'll find them saying thermodynamic equilibrium. They're meaning the same thing. And when we have thermodynamic equilibrium, when you have equilibrium in heat, we are talking about a system that can have a degree of hotness and then a degree of coldness that can counterbalance it so that the system remains existing forever or up to some time we want it to exist. For example, if you look at the sun is in thermodynamic equilibrium in a way that the sun is very hot, but it has some very cold points that try to counterbalance its hotness. So it was discovered that the sun has some very cold regions upon it. Otherwise, if it was very hot and it was burning all through, then there couldn't be any recombination of hydrogen atoms that are making it burn continuously. So at the end of the day, it would burn forever and get done. So it has those cold points which make it be in thermodynamic equilibrium, so that the burning keeps regenerating itself. Then we also have what we call the unsaturated vapor pressure. Unsaturated vapor pressure. The unsaturated vapor pressure, this is the pressure exerted by a vapor which is not in thermodynamic equilibrium with its own liquid. You can say this is the pressure exerted by a vapor which is not in dynamic equilibrium, it's not equilibrium with its own liquid. So as the others are in thermodynamic equilibrium with their own liquid, for this one it's not. The same can be asked as what is an unsaturated vapor. It is that vapor that is not in dynamic equilibrium with its own liquid. Whereas if they say unsaturated vapor pressure, it's the pressure exerted by a vapor which is not in thermodynamic equilibrium with its own liquid. Then these vapors have differences. They can tell you to distinguish between the two vapors. One, saturated vapor, then two, unsaturated vapor. So differences between saturated and unsaturated vapor. So if this is saturated vapor, this can be unsaturated vapor. One, the saturated vapor don't obey gas laws. Do not obey gas laws. While unsaturated vapor obeys gas laws. This one, saturated vapor, it exerts a pressure that has been exerted by a vapor in dynamic equilibrium with its own liquid. Well, for this one, the pressure it exerts is by a vapor which is not in dynamic equilibrium with its own liquid. Then, saturated vapor, because we are saying it's a vapor which occurs when there is a liquid, which is in dynamic equilibrium with a vapor, then it means it cannot occur without a liquid. So this can only occur in the presence of a liquid. This one can occur in absence of a liquid. Then also this one occurs or exists at a constant temperature or fixed temperature, where this one can occur at any temperature. So those are some of the key differences we can mention between the saturated vapor and unsaturated what? Vapor. So they can ask you to distinguish between saturated vapor and unsaturated vapor. Then the other aspect we need to talk about is the origin or the occurrence of or the existence of saturated vapor and unsaturated vapor. And in this case, we want to explain their existence using what we call the kinetic theory explanation, the kinetic theory of matter explanation. And from there, we need to understand or to review, first of all, what does the kinetic theory say or state? Who recalls what the kinetic theory states? Anyone to recall what the kinetic theory states? Let me see if here there was a question on vapors last year. Last year, they never gave a question on vapors. Someone state for us the kinetic theory. Someone who recalls. We have talked a lot about the kinetic theory before. Someone written it, let me see. How about change in volume has no effect on the unsaturated vapor pressure? We are assuming they're in the same volume. Brian Matov was asking, how about change in volume? Has no effect, does it have an effect on unsaturated vapor pressure? If we are assuming they have the same containers or the same vessels in which the vapor or the liquid the vapor has been contained. So if they're in the same containers, then the volume is likely not to change. So that's the assumption we have here. Yeah, this was UNEP 2014. The question was state two differences between saturated vapor and unsaturated vapor. 2 marks. Sketch a graph of pressure against temperature for an ideal gas and for saturated vapor originally at 0 degrees Celsius. We are going to see all that. With the available diagram, let's try an experiment to determine saturated vapor pressure of water, 5 marks. State how the experiment above can be modified to determine a saturated vapor pressure above atmospheric pressure. That was 1 mark. Yeah. So it had around 6 marks. It had 11 marks concerning vapor pressure. I mean, concerning vapors. So I just wanted to confirm to you that the questions can be set, and they can be set just like I've been discussing them, among which they can ask you for the differences between the two pressures. It was 2014. In 2013 was asking for 1. The pressure of an ideal gas is given by a third rho C bar squared, where rho is the density, C bar is the mean square speed. Show clearly steps taken to derive this expression. That derivation of this one of pressure is equal to a third rho C bar squared. It had 6 marks. This was year 2013. State the assumptions made in deriving this expression, 2 marks. So those are 8 marks. Because if someone knows the assumptions taken, then you know how to derive. Sketch a graph of pressure versus volume curve for real gas for temperatures above and below critical temperature. Yeah, so basically most of these items we are looking at, they can be examined. I'll be posting some of those questions with time so that you can take a look at by yourself and handle the questions. Now, the next suggestion here says to give the kinetic theory explanation for the occurrence of these vapors. How do they come about according to the kinetic theory explanation? One, you can consider a liquid that has been heated in a closed container, whereby if the liquid is in a closed container, like this one, and you're heating a liquid which is in there, the most energetic molecules overcome the attraction of the molecules, of other molecules, and they come to the surface. If those balls are showing the most energetic molecules, because they are very energetic, they can change state and move from the shape of being liquid molecules, and they convert to vapor, and they leave the liquid. So when they leave the liquid, they become vapor molecules. So they live like this. Then they can reach the top of the cover of the what? Of the lid of the vessel. So when the most energetic molecules overcome the attraction between the molecules of other liquid molecules, they reach the surface of the liquid, and then they can convert to another state because they're very energetic. So they convert to another state, which is vapor. So they form what they call vapor molecules. When they form vapor molecules, this process is called evaporation, whereby the molecules are converting from a liquid going to a gaseous state, right? So as more liquids turn into vapor, yeah, what happens? The vapor density increases, or the density of vapor goes on increasing. So you'll have so many molecules which have been turned into vapor. So you see a lot of vapor, sometimes you call it steam. So you see a lot of steam, a cloud of steam inside, yeah, which is just above the liquid. Why? Because once you keep on heating the liquid, more molecules are gaining kinetic energy, and more molecules rise to the surface, and more molecules convert to vapor. So you have a cloud of vapor that has been formed as a result of more molecules gaining kinetic energy and more molecules converting to vapor. So it means a lot of evaporation now is taking what? Place. So with that, these vapor molecules, as they rise, I've told you they come and reach the surface of the cover. When they reach the surface of the cover, they are going to collide with the lid, with the cover here on the surface. So they will collide with the walls of the container, or they collide with the cover, giving rise to a pressure. So they put pressure on the cover. Girls and even some boys, most of you, I think, cook. Boys also, you should know how to cook. You never know, those girls might disturb you in the future. So when you put on a lid which is not strong, have you seen kettle covers? Sometimes you start seeing them jumping over. So they're not jumping because the water is pushing them. No, it is because there is a pressure that is coming from the vapor. There's so many vapor molecules colliding with the cover or with the lid are tending to push it up. So the cover is experiencing a vapor what? Pressure. I don't know whether you're following the physics from where I began from. We began from heating the liquid molecules. The liquid molecules gain kinetic energy. The most energetic molecules run away or free themselves from the attraction of the surrounding molecules, and they rise to the what? To the surface. When they rise to the surface, they have enough energy, they convert into another state, which is vapor state or gaseous state, and then they start escaping from the liquid as what? As vapor. When they escape from the liquid as vapor, more molecules are being heated because the heating continues. As more molecules are being heated, more molecules are rising to the surface and converting into what? Into vapor. So time comes when these vapor molecules that have been formed collide a lot with the walls of the container or the walls of the cover of the vessel. And in that case, they are going to exert a pressure as they collide more and more with the container. That pressure they exert is what we are calling the vapor what? Vapor pressure. Vapor molecules also collide with others, losing the energy, and losing some energy or losing some of the energy they had, and they re-enter the liquid. And this process is called condensation. Now, as these molecules are going up, the vapor molecules, they are going to collide with some other molecules of vapor. Yeah? When they collide with some other molecules of vapor, they lose some of the energy. While others, when they go and collide with the walls of the container up there on the ceiling, they still change state because they have collided. You know, collisions sometimes, if they are not elastic, collisions which are inelastic, they lead to loss of what? Energy. So when they collide and get stuck on the cover of the container, they lose some of the energy, so they liquidify. That is why when you open a lid of a cover of food, of sauce, it has droplets clinging on the top of the cover. Those droplets are coming from vapor molecules, losing some of their energy as a result of collision with the cover of the container. Are we getting the physics? I might not write all this, but I will send the writer, but I need to discuss and be with you, whereby in case there is a concern, please you raise it. So at that instant, we are saying we are experiencing condensation. Why are we experiencing condensation? Because some vapor molecules collide with other vapor molecules. Other vapor molecules collide with the walls of the container. We are assuming now the lid, the cup of the vessel of the system. We are calling it a container. So we can say they are colliding with the walls of the container that is on top. They are colliding with other molecules of vapor. As they collide, they lose energy. When they lose energy, they condense back to the liquid. And they condense in form of droplets, which fall back into the what? Into the liquid. Now, at that instant, my network wants to misbehave. So I was saying at that instant, when the rate of evaporation is equal to the rate of condensation, yeah, then at that instant we can say that we are obtaining what we call thermodynamic equilibrium, or we are obtaining dynamic equilibrium. Yeah. So at the instant when the rate of evaporation is equal to the rate of condensation, yeah, then we say, or we shall have said that we have reached what we call the thermodynamic equilibrium. And at that instant, the vapor which is experienced, or the vapor which we have, we shall say has been saturated, or the vapor will have been what we call saturated. So the vapor is only saturated if the rate of evaporation is equal to the rate of condensation. But when does this condensation occur? Condensation occurs when we are having some of the molecules of the vapor molecules colliding with other vapor molecules and they lose what? Energy. Or when the vapor molecules collide with the walls of the container at the top and they lose some of their energy, condensing back into the liquid. When they collide, one should ask, how do they lose the energy? It is because energy is directly proportional to temperature. The vapor molecules are kinetical, have more energy because they are at a high temperature. That's why steam is at a high temperature. Yeah? I told you an example of you cooking. You use rice. When you put a piece of chicken in rice, which rice is just drying up without water, it is being cooked. That rice is burning or is cooking at latent heat of vaporization. So if you put anything there, even if you put a head of a goat, for example, if you have a very big saucepan of rice, 100 kgs, and you put the head of a cow, when the rice is just being ready, even if the rice is ready, and you just leave it there with that steam, that head of the cow can get ready. Why? It is going to be cooked with vapor. You know, when I'm cooking, I put in a lot of physics. Yesterday I was roasting meat and chicken. Then I could roast them a little. Then I could wrap them in foil paper. And then I could put them on top of the charcoal. And then these guys were like, but this meat is raw. What? I told them, you do not know the physics behind. They are going to burn. They are going to get ready using latent heat of vaporization. The vapor is going to come and cook this meat and this chicken entirely within the wrapping paper, so it will get ready. It is the same principle they use for cooking luombo. Luombo gets ready because of vapor. It is cooked with vapor. It's not cooked because of boiling water in the saucepan. No, it's vapor which is inbuilt within the luombo. That vapor has nowhere to escape. So it works upon whatever is inside, losing the energy to whatever is inside, hence whatever is inside gets ready. So I was still giving you this illustration of how the rate of evaporation and condensation becomes equal. When the rate of evaporation and condensation is equal, I was saying condensation comes from loss of energy. We lose energy if and only if the energetic molecules, which are in vapor form, have collided with each other, or they have collided with the walls of the container at the top. But where does that come from? It comes from those energetic molecules which are within the liquid which is being heated or boiled, escaping from other liquid molecules, raising to the surface of the liquid, and then escaping to another form in form of vapor. But as they escape, more molecules are doing what? Doing the same, coming up. So at the end of the day, they will collide and lose some energy. Others will collide with the walls of the container, hence condensation will occur. So at the rate at which condensation, the rate of condensation being equal to the rate of evaporation, this would imply at that instant that we are experiencing a pressure, which pressure is called saturated vapor pressure, coming from, we shall have experienced what we call a saturated vapor, and that vapor, the pressure it exerts is what we shall call the saturated vapor pressure. Therefore, the density of the vapor and the vapor pressure are maximum at that instant. Yeah? At the instant when we have the rate of condensation and the rate of evaporation being the same, then the density of vapor and the vapor pressure are at a maximum. At that, when they are at a maximum, then they are occurring at what we call a constant what? Temperature. Remember, I said in the differences, saturated vapor occurs at a constant temperature. So if the density of vapor and the vapor pressure are maximum, it means they are no longer changing. If they are no longer changing, that means this is occurring at a constant temperature. And the pressure they're exerting at that point is what we have called the saturated vapor what? Saturated vapor pressure. Any questions on the saturated vapor pressure and saturated vapor, how it comes about? Any question? They can ask you another question like this one. There is a lot of explanation that goes around this area. So we need to listen to a lot of physics that is occurring. They can ask you using the kinetic theory. Using the kinetic theory, explain the effect of temperature. Explain the effect of temperature on saturated vapor pressure. Saturated vapor pressure at a constant volume. So my friend was suggesting something about volume. I told you we had assumed that the volume is what? It's constant. Okay. So firstly, they're asking us to use the kinetic theory to explain the effect of temperature on saturated vapor pressure. How does temperature affect saturated vapor pressure? We have seen in the earlier discussion that for saturated vapor to be experienced, it is experienced when, sometimes, by the way, what the word means with dynamic equilibrium with its own liquid, it means the vapor is in contact with the liquid. That's, I think, another easier way to understand it. We have seen that for saturated vapor to be experienced, formed, we should have the rate of evaporation being equal to the rate of condensation. Yeah. So when the temperature increases, remember temperature is directly proportional to the kinetic energy. When temperature shoots up, the kinetic energy also, or the average kinetic energy of the molecules also increases. And what happens? I told you the most energetic molecules rise up to the surface of the liquid and leave the liquid, leaving behind the less energetic molecules. When these most energetic molecules keep getting out more and more, they increase the rate of evaporation. Right? When they increase the rate of evaporation, they will distort dynamic equilibrium momentarily. What does that mean? It means that there will be a reduction of the liquid molecules in the liquid. This is when we get, have you ever heard of a situation where your parents say, you're boiling that to get done? You boil something, for example, you boil water non-stop and it's not getting done, it's not getting stopped. The heat is still continuing to flow out. The water does not splash out. But what happens, the water converts into vapor. If it's not covered, it converts into vapor and escapes in form of vapor, escapes. At the end of the day, you'll come and look at the volume of the water remaining when it is very small. It can even burn up to morning. If you burn it, if you heat it up to morning, it can burn until the saucepan gets dry. So it means that as evaporation takes place, you remain with less liquid what? Molecules. When you have less liquid molecules, it means dynamic equilibrium is going to be reduced. That's why I'm saying that when the temperature increases, the average kinetic energy of the molecules also increases. The most energetic molecules leave the liquid surface, and this will increase the rate of evaporation. When the rate of evaporation increases, dynamic equilibrium is momentarily distorted. So the increase in the rate of evaporation increases the density of vapor of the liquid. When the density of vapor increases, it means we are having so many vapor molecules coming up. You have a cloud of vapor molecules. If there are so many, it means they are going to collide a lot with the fellow vapor what? Molecules. And they will collide a lot with the walls of the container above there. Not so. That would imply if the rate of evaporation has increased, then the rate of collision is also going to increase, which will bring about an increase in the condensation. Therefore, the rate of condensation also will increase. Dynamic equilibrium is going to be attained at higher value, thus increasing saturated vapor pressure. Now, because what happens is, remember, to get dynamic equilibrium, we attain it when the rate of evaporation is equal to the rate of what? Condensation. When you have a lot of evaporation taking place, it means you need to have a lot of collisions, meaning you'll have a lot of collisions in order to get a lot of condensation. So at that rate, when the rate of condensation is equal to the rate of evaporation, that is when we shall attain dynamic what? Equilibrium. So it means you require to get that equilibrium at a very high temperature. So the more you increase the temperature, the higher the saturated what? Vapor pressure. So with that, you would have explained how saturated vapor pressure varies with temperature. Let's talk about some graphs. A graph of saturated vapor pressure against temperature. A graph, unless someone has a question before, of saturated vapor pressure against temperature. So this is going to be, this is our graph, then this is temperature, then this is saturated vapor pressure. You know, saturated vapor pressure does not start from somewhere. So there is a pressure you have, there is a value of pressure you have to first reach on. So this is the shape of the graph. Then the second graph, a graph of pressure against temperature for an unsaturated vapor pressure. A graph of pressure against temperature for unsaturated vapor pressure. So for the unsaturated vapor pressure, if this is the pressure, then it's a straight line graph. Then they can ask you to draw a combined graph. The graph of the graph of pressure against temperature for both saturated vapor pressure and unsaturated vapor pressure. So people, make sure that you can visit the internet and read about some of these items. It is very healthy if you go to Mr. Google and type in saturated vapor and you read about it from the internet. It will give you an advanced area, examples, applications of some of these items. My pen has slipped. I want to draw a backward what? Backward stretch of the curve. So if you stretch back that line, this should be negative 273 degrees Celsius. Then this will be 0 degrees Celsius. This will be temperature, degrees Celsius. And this will be pressure. So there was a question here which was saying what? Something about a graph. Sketch graphs of pressure against temperature for an ideal gas and for saturated water vapor originally at 0 degrees Celsius. Sketch graphs for pressure against temperature for an ideal gas and for saturated water vapor originally at 0 degrees Celsius. Okay. So that question, the answer is these first two. Okay. And there is another explanation they can ask you for, which can be of the form use the kinetic theory to explain why saturated vapor is not affected by a decrease in volume at a constant temperature. Now, for this case, question is saying, use the kinetic theory. Use the kinetic theory to explain why saturated vapor pressure is not affected by a decrease in volume at a constant temperature. So to start with, one should know when the volume has been decreased, yeah, or reduced, the space above the liquid reduces. If initially you had something like this, then it has been reduced to this. If the liquid was a little bit down, now the liquid would raise. Yeah? When the liquid rises, the space above becomes small. Here the space above was big. Here the space now is what? Small. So the space above the liquid reduces. When the space above the liquid reduces, what happens is the vapor molecules are going to be clustered together, so many, like this. Yet here, they were like this. So these ones form what we call, what? A high vapor density. So the density of vapor increases when you reduce the volume of the container. And that means when the vapor density increases, the vapor condensation also will increase because so many vapor molecules are going to collide with each other. And thus, this will also increase the saturated vapor pressure momentarily. Because you have reduced the volume, increased the vapor density, increased the rate of collision, increasing the condensation rate, and thus you have increased the saturated vapor pressure. Now, because they say temperature is constant, so since temperature is constant, the rate of evaporation is the same, it is not changing, because the same rate at which the molecules are gaining kinetic energy to evaporate, it is still the same. So their evaporation is a what? It's a constant. However, there is an increase on condensation, as we have seen. Condensation is increased because a lot of molecules are colliding with their fellow molecules of vapor. So a lot of condensation is occurring. So this rate of condensation is occurring without an increased rate of evaporation. So we are having an increased rate of condensation, but with a constant rate of evaporation. So what does that mean? This will mean that there is going to be a decrease in the vapor density. When this decrease in vapor density occurs, it will cause the rate of condensation to decrease. Why? It is because we do not have so many molecules coming up into vapor as we have been having the rate of condensation taking place. So many molecules will lose their energy and leave a vacuum or leave a space of molecules which are unmatched. So in that regard, we shall have a decrease in the vapor density, and also shall have a decrease in the rate of condensation. And thus, also saturated vapor pressure will decrease. So this makes the dynamic equilibrium to be restored to the original value as a result of having a decrease in condensation. Thus, the volume change has no effect on saturated vapor pressure. So they ask you, you're going to have this right up, and you'll get to know why when you change the volume, it does not actually affect the saturated vapor pressure. It's because time comes when the rate of condensation is so higher than the rate of evaporation. And what will happen is the condensation will occur drastically, and it will reduce the number of molecules of vapor that are meant to be colliding until when the time comes when they go back to their original rate of condensation, and thus we would have maintained the saturated vapor saturated vapor pressure. Otherwise, it does not occur in a sense that when it occurs and the other molecules condense back to the liquid, they don't come back. No. Time comes when they come back to the same rate, and this we attain equilibrium again, and thus we maintain saturated vapor saturated vapor pressure. Another graph we can talk about here is a graph of pressure against volume for saturated vapor. A graph of pressure against volume for a saturated vapor. Because you have seen that the saturated vapor pressure does not get any change or any effect, so it will be a constant line with this as volume V. Then a graph of pressure against volume for an unsaturated pressure, unsaturated vapor. This is case 1. For case 2, for an unsaturated vapor, its graph will take on this shape. So for it will be affected by a change in volume. If you change the volume for an unsaturated vapor pressure, for an unsaturated vapor, which is not in dynamic equilibrium with its own liquid, its pressure will change. Okay, so far we have had the following. We have the experiment. They can ask you to describe an experiment to verify variation of saturated vapor pressure with the temperature, or to describe an experiment how saturated vapor pressure of a liquid at various temperatures can be determined. It has a very sensitive illustration, which you'll see. Whereby it has a gas bulb, round bottomed flask. Then it has a thermometer. As a thermometer. And the vapor escapes through these pipes. Well sealed. Then it has a condensation point or condenser here. And we have here cold water in. Then here hot water out. Then this one proceeds to another chamber, which has a manometer. Which is in form of a U-tube. Which is open on one end. This is what we call an air reservoir. Then this junction is connected to the pump. Which is to the vacuum pump. Or it can be a bicycle pump. And when we are marking these illustrations, we normally we first consider the entire diagram drawn correctly. The diagram is drawn wrongly, don't score any mark. So we consider the diagram drawn correctly, and then we assume you have any 4 correct points. Those are the ones we give the what? The halves. And then you get the marks. If you draw this diagram like mine and stop there, everything is wrong. Firstly, there is no water you're heating, or there is no liquid boiling. And it is being boiled in a way that it is being heated. So this is the boiling liquid. So any 4 correct labeled parts, you score a mark. This is a flask. And this one is a saturated vapor. Okay, so in that regard, the pressure above the liquid, P, is varied to some desired value below the atmospheric pressure. So they vary it by adjusting. There is a tap here. So you vary it until it is below the atmospheric pressure by means of a vacuum pump. Yeah. Then the water is heated until it boils. So you first make sure that the pressure is just below the atmospheric pressure. Then go ahead and heat the liquid until the temperature of the vapor, capital T, is recorded. Then go ahead and make sure that that vapor which has been formed is condensed, and you let it return into the flask. So how does it get returned into the flask? It gets returned into the flask by when the vapor comes through here. When the vapor comes through here like this, it will condense through here and then return back to the liquid. Return back to the liquid as droplets. So when it returns back to the liquid or to the flask, we do that in order to prevent pressure buildup. When you do that, you get the pressure, the maturity height in the difference in these maturity levels. So you get this difference here, small h. There is atmospheric pressure out here, capital H. So you get that difference in maturity heights. So that difference in maturity heights can be measured, whereby whereby you can have the pressure as coming from the atmospheric pressure. Because this side is lower, it means this pressure up here is smaller. Yeah, so it means the atmospheric pressure, which is PA, I'm assuming PA is the atmospheric what? Pressure. When you subtract off H rho G, the pressure due to the height in the other limb, then you're getting the pressure of the vapor. So by means of replacing the vacuum pump with a bicycle pipe, we can do that also to, remember there's a question I asked earlier. There's a question I saw. They said, describe the experiment, and after the experiment, they asked us to, there's a second question I saw, which they said they can vary. I still have it. Where is that question? Hey, it says, with the aid of a available diagram, describe the experiment to determine saturated vapor pressure. So this is the saturated vapor pressure, P. Then they said, state how the experiment can be set up or may be modified to determine saturated vapor pressure above the atmospheric pressure. You can do that by replacing the vacuum pump with a bicycle pump. So you can replace this with a bicycle pump. When you do that, you have modified the saturated vapor pressure to be above the atmospheric what? To be above the atmospheric pressure. So let me send the write-up for this so that you can have all of them written down. And then, like I've said, visit the internet for more readings. Then next week, we shall introduce calculations on this, on the pressures. Okay. But you read more about them. Then after their calculations, we shall go to boiling and evaporation as items on their own. Okay. If time allows, then we can go to other items. Any considerations you need to take? No further questions. I think we can stop here. Let me send the questions right away. I mean, the work, the notes. Send the notes right away. So please don't hesitate to visit the internet and read more about these. These explanation items require a lot of research. So go do some research on the internet or visit some books like we sent to you already. Okay.